Hello guys, and welcome to yet another video. We're gonna skip through all of that and just get straight to problem solving, right? This is a very new and interesting paper that I'm excited to solve with you guys. Okay, starting with the first question. We've been asked to state what is meant by a vector quantity. So we want to understand what is meant by a vector quantity. Now, a vector quantity is basically a quantity that has magnitude and direction. So I'm just gonna go right here and write that. So it's a quantity. Right, a simple example is displacement. If I were to ask you, go from point A to point B, what's going to happen is you're going to move a certain distance, let's say 20 meters. 20 meters is the magnitude, and the direction can be due east, due west, or to the right, or to the left. So you have two components, magnitude and direction, which are very important when explaining what a vector quantity is. We also have scalar quantities. These are quantities that don't have direction. All they have is just magnitude itself. Right? Let's move on to the second part of the equation. We're given a sphere that falls vertically through a liquid that has density 830 kilograms per cubic meter. The sphere has that radius and a constant velocity of that. And we've been told that the drag force D acting on the sphere is given by that equation. Determine the SI base units of that constant, the property of liquid. Right? Okay. So whenever you're asked to determine the SI base units, I want you to use this trick, right? It always works all the time. What you're going to do is you're going to make the thing that you want to find the SI base units for the subject of the formula. So using that method, I basically know that mu is going to be equal to D over 6 pi RV, right? So the base units, so you put those little square brackets that sort of show that I want to find the units, will be equal to the units of D divided by the units of R multiplied by the units of V. That's basically how you can be able to find the units of that particular constant itself. Now, what we're going to do is, if I want to find the units of that constant, so the units of D, I know D is the force. So you're gonna ask yourself, force. I know force is actually mass times. So force is actually mass times acceleration. So what are the base units for mass? What are the base units for acceleration? That's what you're asking yourself basically. So I know that the drag force is therefore going to be the units for mass. That's kg. Acceleration is ms to the power of -2. All of that divided by, what are the units for R? R is basically my radius, that's R meters, multiplied by my velocity, that's meters per second, that's m squared, that cancels out. I'm left with kg m to the power of -1. I have s to the power of -2 divided by s to the power of -1. That's going to give me s to the power of -1. You've done indices, right? If you still remember. If you don't, it's going to be a little bit tougher to answer these kind of questions. Okay. State an equation to show the relationship between the magnitudes of the weight W, the drag force D, and the upthrust acting on the sphere. So I'm going to go here. I know that my weight acts down, right? So that's a given. I know that my weight is going to be acting down. So down, I'm going to say my weight. Okay, cool. Now I know that upthrust tries to bring an object up, from the word up. Thrust, right? It's the thrust that tries to bring an object up. From Archimedes' principle, we've understood what upthrust actually is. So I know for a fact that my upthrust is going to be acting up, right? So this is the direction that I have my upthrust. Okay, so now I'm left with the drag force. The drag force basically opposes the motion of an object. It's a force that opposes the motion of an object. So it's going to oppose, the object is trying to move down, the drag force is going to oppose that, and it's going to be acting up. So upwards, that's where I'm going to be, okay, let me change the color of that. Upwards, that's where I'm going to experience my drag force. Now we can see that my weight will be equal to my upthrust plus my drag force. So the two forces, or the three forces rather, are acting in different directions. Two are acting up and one is acting down. So what we're then going to do is basically say my weight, W, is equal to upthrust plus the drag force, right? Okay. Next question. The volume of the sphere is 4.6 cubic centimeters. The drag force is that. Calculate the weight of the sphere. Now, what I love about physics is that these questions are so related. In the last question, you had a relationship between weight, upthrust, and drag force. You already know what the drag force is, so giving me the volume means I have to use that somehow to find the upthrust. Now you're going to ask yourself, what formula can I use to calculate the upthrust? Now I love this because upthrust has a special little formula that we use. Upthrust is actually equal to rho g times v. Right? So the rho is not the density of the material itself, but rather the rho is the density of the fluid itself in which all of this is happening. So I know that my rho in this particular case, if I look at my scenario over here, my density is 830. So I'm basically going to say 830 multiplied by g, that's 9.81. My volume is 4.6 times 10 to the power of negative 2 cubed, right? Cm, that's 10 to the power of negative 2. I want to convert that to meters cubed because there's that little 3 over there. Do you get it? So my upthrust force is basically just going to be 0.03745,458. That's what my upthrust force equates to. Now, in order to get my weight, I therefore just say that my weight is basically going to be equal to my upthrust plus the value of d, right? Plus the value of d. But I already now have the value of upthrust and the value of d. Both of them I have them. So it's just going to be 0.32 plus 0.03745, and that's going to add up and give me 0.36 to 2SF. Why 2SF? Because you're looking at the least amount of significant figures in your raw data. For example, the volume is 4.6. It has two significant figures. So I would expect that your answer also has two significant figures, as Cambridge would expect. So we're going to put it down here, 0.36. Moving on. Define momentum, right? A definition question. Easy enough, just a recall question. So momentum is basically, right? That is what momentum is. You have an object, let's say a vehicle. What is the mass of that vehicle? And if it's moving at a particular velocity, let's say 20 meters per second, the product of the two, the mass and the velocity, gives you the momentum of that particular object itself. That's basically what momentum is. Part B, a child stands on a scooter on horizontal ground. The combined mass of the child and the scooter is 16 kilograms. So the child starts from rest. You have a child on a scooter on the ground and the mass is 16. The child is starting from rest, pushes for like 1.1 seconds, and the speed after pushing is 0.60, and want to determine the average resultant force. So you have to know what a resultant force actually is. So a resultant force, or force in general, is the rate of change of momentum. So for momentum to change, you need a force. That's Newton's second law, right? So in order for you to change the momentum, you're going to have to apply a force. So by definition, a force is basically the change in momentum, don't mind that little p, it's a sign for momentum, divided by the time interval in which that change has occurred. So my momentum started at the mass times the velocity, which was 0. Now it ended to the mass times 0.60. So I know that my change in momentum is basically going to be equal to my final momentum minus my initial momentum divided by time. And in this case, my initial momentum is actually 16 times 0.60 minus 0, because the initial momentum itself is 0. Divided by my time, which is 1.1, right? You do the math, you divide the whole two things, and you should be able to get around, please do it on your calculator, guys. You should be able to get around 8.7272. On average, that's 8.7 newtons. So you put your answer here, 8.7 newtons. Easy enough. Later, the child in B travels down a slope at a constant angle to the horizontal, as shown in that figure. So the child now is moving on a slope. Things have changed. At A, her speed is that, she has a constant acceleration of that. After a time of 3.7 seconds, she reaches point B, and want to calculate the distance x that the child has traveled along the slope from A to B. So that's what I want to do, right? So in order to do that, it's going to be fairly simple. Look at what you're given, right? I want to teach you problem solving. Look at what you're given in the equation. You're given speed, acceleration, time, and you want to find distance. Ask yourself, how are all these variables, these four variables, related? What equation can you use to relate all these different things? And your mind should be like constant acceleration. So what equations should be used here, right? So what your brain is doing is it's looking at all these different connections, trying to piece them together to have a formula that works. So you must know this formula, right, guys? Come on. S is equals to ut plus half at squared, right? So x will be equal to ut plus half at squared. So my initial speed is basically 0.60, my time 3.7 plus 1 half, my acceleration 0.85, my time 3.7 squared. You're going to get a value of x that's around 8.03825. Again, two significant figures. The raw data, for example, 0.60 has 2 SF, so I should be able to get 8.0 meters. So 8.0. Okay, cool. Moving on. At point B, the child in C applies the brake with a constant force, right? So the child on a scooter steps on the brake to maintain a constant velocity. Point C is 18 meters from point B, right? And we're given that the work done by the braking force is 250 joules. We want to determine the magnitude of the braking force. Now, it's very important for you to connect. Again, physics is about problem solving. How can you use the information that you have to solve a new problem that you have been presented with or that you have been given, right? So we're given the work done to be 250, and you've been asked to find force, but you're given distance. Ask yourself, how are these things related? Well, what I know is that my work done is equal to my force multiplied by my distance, right? Or my displacement if you're fancy, right? So I now know that my force will be equal to my work done divided by my displacement. So in this case, my force will be equal to 250 divided by 18, right? Very simple. 13.888589. That's going to give you 14 newtons. Okay. On Fig 2.3, sketch the variation of the kinetic energy, okay, and the scooter with distance traveled from A to C. Numerical values of kinetic energy are not required. Okay, cool. So we've been asked to plot a graph, right? I want you guys to be very mindful of what plotting a graph actually entails. Plotting a graph revolves around equations. A graph is a way in which you can visually show an examiner that you know what an equation looks like. For example, if you have a linear graph, you know that it's trying to show a particular equation, a relationship between y, x, or y, x, and z, and all of that, right? If you have a quadratic equation, that's the same. So your first point of contact is to ask yourself, what equation can I create that relates kinetic energy with displacement or with distance? So if you look at it, let's start from 0 to x. So from 0 to x, it's here. From 0, this is 0 over here. X ends over there, right? So what we're going to do is I'm going to use a very typical equation that you know. Kinetic energy is actually 1/2 mv squared. And I ask myself, can I substitute the value of v and input displacement, right? So it's not rocket science. The question that you're asking yourself is, how can I put distance in that equation for things to make sense? So I know that x is actually equal to if we say v squared is equal to u squared plus 2as, I know that v squared, the velocity at a particular point in time, will be given by that equation. So I can substitute v squared in that equation. My kinetic energy will be equal to 1/2 m u squared plus 2as. In this case, S is X. So my kinetic energy will be equal to 1/2 mu squared plus half and 2 cancel out m a s. So my kinetic energy will be equal to m a x plus 1/2 mu squared. But this is not rocket science. I'm not doing anything fancy. I'm just substituting an equation to see the relationship between kinetic energy and x. And you can see that this is a straight line relationship, right? Look at it, guys. It's a straight line relationship. A line with a gradient of ma and a y-intercept of half mu squared. You can see that, right? So this is an equation of a straight line, right? And it has a y-intercept. So this is a y-intercept. So I would expect your graph to start from here. Let's assume, right? You don't have to have numerical values because they say they're not required. So that's just half mu squared. You know that that's my y-intercept. And then that kinetic energy is going to rise and it's going to be a straight line from there up until there, like so. Right? That's basically it. And then from x to x plus 18, you look for what's happening to the velocity. Can the same equations still apply? If I go here, look at this. To maintain a constant velocity. So if you have a constant velocity, does the kinetic energy change? Really, guys? Does it change? It doesn't. So the kinetic energy remains the same because the velocity itself is the same. So I would expect my kinetic energy to therefore just plateau and just be constant like that, right? So I know that I go from 0, I go to x, and then it plateaus. My kinetic energy remains constant. My velocity plateaus and just remains the same. Let's move on. Question 3. I hope it makes sense. So graph sketching, remember, ask yourself, what equation can I use and how can that equation help me to be able to solve the problem that I want to solve? Question 3. The variation of stress with strain for a material, metal P, is shown below. So we have stress on this axis and we have strain on that axis, right? You strain something, it gets stressed. What's going to happen? You stress something, it gets strained. Sorry, it works that way. Okay, point E is the elastic limit of the material. That is where it stops going back to its original point. That's what elasticity means. It has to go back to its original point. Elastic limit, that's when elasticity ends. So use fig 3.1 to determine the Young modulus for P. Very easy. I know that my Young modulus is the ratio of stress to strain. Stress over strain. That is essentially what my Young modulus is. What is the ratio or the relationship between stress and strain? So if I want to make that relationship, if I want to better understand how those two variables are related, we're basically going to be able to say 2.4. Find a point. Find a point that you want to use. In this case, I want this point. Looks very easy to use, very convenient. This little point over here. You know, I'm trying to be fancy. So at this point, I have a strain of 1% and a stress of, is that 24? 24. Okay. So my stress is basically 24 times 10 to the power of 7. My strain is 1 over 100. I think I didn't tell you guys. I don't think you were ever taught this. I don't understand why textbooks do this. But whenever you're given strain in percentages, right, 5%, 10%, don't use it as it is. Strain is a ratio between extension and original length, right? So if they give you a percentage, 1 over 100, what it's telling you is essentially, hey, right, 1 over 100 is the ratio itself between the extension and the length, right? So you're not going to use the percentage, you're going to use that ratio. And we know a percentage is just a ratio multiplied by 100. That's why I have to say 1 over 100. And if you punch that in a calculator, you're going to get 2.4 times 10 to the power of 10. So you can see that E is the gradient of that graph, actually. Okay, on the line, fig 3.1, draw across a little x right? To show the limit of proportionality. Guys, this is as straightforward as it sounds. The limit of proportionality, the point where proportionality ends. Don't overthink it, right? So where does proportionality ends? Where does the direct proportionality, where stress and strain are proportional, end? Would you look at that? The little dot that I put over there, that's actually where it ends, right? If I put an X here, because after that, we have this kind of weird relationship happening where it's no longer proportional, as you can be able to see. So I label this point Q. Follow instructions. You're about to be like me, right? I didn't follow instructions here. So you have to label your point as Q. So I go here and I label my little point over here as Q. That'll be it. Okay. State the conditions necessary for an object to be in equilibrium. For things to be equal, we have two conditions that must be met. The resultant force in any direction has to be 0, and the resultant moment or torque about any point has to be 0. So the thing shouldn't turn in any direction, and the object shouldn't have a force that it's experiencing in any direction as well. So we're going to put that in words. And that'll be it. Okay. Part C, a wire is used to hold a uniform shelf. We're given a little shelf here. We have a little cup. Wow, very nice setup. I like it. So the wire is connected to the midpoint of the shelf, AB, at an angle of 50 degrees. The shelf is attached to the wall by a hinge at A. The length of the shelf is that. Its weight is that. A cup is resting on the shelf at a distance of 0.12 from B, right? So if it's 0.12, we know that the distance from here up until here would just be the difference of the two. Might as well just calculate it. You never know. You never know when it's going to be important. So 0.65 minus 0.12, that looks to me as 0.53. We're just going to have it just in case. By taking moments about A, determine the tension in the wire. So the wire is going to be under tension, right? It's going to be tensile. Okay. So if I go here, I label this my tension. I'm going to resolve it, guys. I'm a little fancy. I want to resolve my forces. Okay. I have that direction. Okay. I have that direction. Okay. So if I turn away from the angle, if I turn away from my sins, turn away from an angle, I arrive at T sine 50. Right? If you don't want shortcuts, this is the opposite. Remember, if I were to draw this, these two things are the same because they're in the same direction, pointing up. They've just been translated to the side. So it's the opposite. This is the hypotenuse, opposite and hypotenuse. That's sine 50. So sine 50 is T over the hypotenuse, which is that T thing, right? So you end up having your opposite as T sine 50. Does that make sense? Okay, why am I doing this? Because I need a perpendicular distance between the line of action of the force and the pivot itself, the line from the pivot. I need them to be perpendicular. So if I have this, I now have the weight of my shelf acting in the middle. That's 33 newtons. I now have my little cup over here with its weight of 1.5 newtons also acting like that in that particular direction. So I'm going to work with those two things and be able to arrive at a particular answer. So if you look at this, the two weights here are providing my clockwise moment, and this little tension over here that's going up in this direction is actually on its own providing the anti-clockwise moment, right? So we know that the principle of moments, what does it say? The sum of the anti-clockwise moments should be equal to the sum of the clockwise moments. That's exactly what the principle of moments says, right? So moment is just force times distance, force times distance, force times distance. So if I go here, for the anti-clockwise, I have T sine 50 times the distance. It's in the middle. I've been told that the y is connected to the midpoint. So the distance is 0.65 divided by 2. I did that calculation for you, so you don't have to. You can thank me later. Okay, so we get 0.325. That's going to be equal to, we look at the clockwise moments, we have 33 multiplied by 0.325 plus, we have 1.5 multiplied by 0.53. So if I want my tension T is now just going to be 33 times 0.325 plus 1.5 times 0.53, divide all of that by 0.325 multiplied by sine 50, and we're able to get my tension, which is going to be equivalent to 46. Punch that all in the calculator and do that separately. Don't just punch it all at once. You're going to make a lot of errors. I did that whilst I was calculating this, so be very careful of that. So 46.2716761, something like that. You're going to get 46 newtons to SF. Remember my rule, 46. Okay, cool. The stress in the wire is that determine the radius of the wire itself. Okay, you're going to ask yourself, what is stress? Right? What is stress? Not you worried about your upcoming exam. I know that's stress, but in this case, that's not going to be it. Stress is force divided by area, right? I know you're worried about your exam, but don't worry, everything is going to be okay. Physics is fun. Physics is fun. Area is equal to force divided by stress, right? Okay, cool. So if I go here, my force is going to be 46, was the tension itself is the force in this context. Remember, use the raw answer. We can use these little calculated answers as well. That's still okay. 271666761 divided by my stress, 1.5 times 10 to the power of 7 pascals. Right? And I know you're stressed like this, right? A lot of stress is on your back, but no, don't worry. Don't think about it too much. Everything's gonna be okay. Times 10 to the power of -6. Okay, cool. So this is my area, right? But what is area? Well, for a wire, area is actually pi d squared over 4. So area is actually pi d squared over 4. So if I want to find d, right, d is going to be equal to the square root of 3.084 times 10 to the power of -6 times 4 divided by pi. Right? I'm just making stuff subject of formula. And I'm going to get 0.01981832 blah 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 blah. And I know that radius is actually diameter divided by 2. So I'm going to say 0.01981832 divided by 2. And that's going to give me 9.9 times 10 to the power of -4. Cool. 9.9 times 10 to the power of -4. Okay. More items are added to the shelf, doubling the stress, right? The stress has been doubled. The wire is made up of material of the same metal from A, metal P. Use Fig 3.1 to state and explain whether the wire will behave plastically or elastically as the stress doubles, right? So if I go on my graph here, this is my elastic limit. If I go here, this is my graph 3.1. This is my elastic limit. And my stress is 1.5, somewhere over here. Right? So if you were to double, it's basically going here. Have I reached this elastic limit, guys, just by doubling the stress? I haven't. I haven't reached that elastic limit. So what it basically tells me, what I'm getting from all of this, is essentially, even if the stress is doubled, the elastic limit is not reached. Okay, that's very, very important, as the new stress itself is less than the stress at elastic limit. So even if you double the stress, it's not going to reach the stress that's required for the elastic limit to be exceeded. You're not going to stress it more than enough for it to, not return to where it started. So I can therefore say the wire therefore behaves elastically. right? In that whole process, the wire would therefore just behave elastically. Does that make sense? I hope it makes sense. Okay. With reference to the direction of transfer of energy, compare the oscillations of transverse and longitudinal progressive waves. So I made a very fun video on waves. I really love this topic. I would highly recommend you check that out. You're going to enjoy it as well as I did making it. But basically, we want to compare the oscillations of transverse wave and longitudinal progressive wave. So what are we going to say? Longitudinal waves have oscillations that are parallel to the direction of transfer of energy, whilst transverse waves have it perpendicular to the propagation of energy. Okay, we're given a pipe that is open at one end, a pipe that is open at one end, closed at the other, with a piston. The piston can slide freely and is at a distance of that from the open end of the wire. A loudspeaker is positioned near the open end of the pipe and it emits sound wave of a single constant frequency. A stationary wave is therefore formed in the pipe as illustrated below. Okay, draw a letter to represent an antinode. Okay, so if we want to represent an antinode, we're going to just draw a little letter A over here, big letter A, to represent an antinode, right? A node is basically here. Okay, but that wasn't asked for. The speed of the sound in air is 340. Determine the frequency of the sound wave. Okay. What's the relationship between speed and frequency again? V is equals to f lambda. So f is actually v divided by lambda. So I have 340 divided by lambda. Okay, now my task is to find lambda. Do I have enough information to do that? Okay, I actually do. I have 4.5 times 10 to the power of negative 2 over here. So if I think about it, what can I do here? Okay, so I have a node at one end, and then I have an antinode directly. But I know I can continue like this. This is an entire lambda, right? All of this is lambda. Okay? All of that. So let me put it a bit nicer. All of this is lambda. Okay. But all I'm given is this length over here. Let's say it's x. How many x's do I have? I have 1, 2, 3, 4. I have 4 x's. So I know that my lambda is just going to be 4x. And I have the length of x, which is just 4.5 times 10 to the power of negative 2. So that's the length of that. So here, I'm going to have 340 divided by 4 times 4.5 times 10 to the power of negative 2. You do the math, and you should arrive at 1900 to 2SF. Again, 1900, that's 2SF. The zeros after that are not significant. So I'm going to have 1900 hertz. Okay, cool. The piston is moved to the left. So I take my piston and I move it to the left. This is the left, right? So you take a piston, you move it to the left. The frequency of the sound wave emitted by the loudspeaker then changes so that a stationary wave is formed with the same number of antinodes as in that figure. Stated and explain the changes made to the frequency of the sound wave. So let me simulate it a little bit here for you guys so that you see. That's the whole point of a video, to do these little simulations. Okay, so what's happening is we have scenario A where this is happening, right? So let me put that down. That's scenario A. Okay, then we have scenario B where we have moved it further to the left. So something like this. So I've moved it further to the left like this. Okay. But I've still formed the same number of antinodes, which was 1 to begin with. So I've still formed the same number of antinodes. But what you can see is V is the same. So this is scenario B, right? And I know that this is still my distance x. This is still my distance x. Lambda is actually 4x. So from scenario 1 to scenario 2, the value of x itself has increased. So the value of lambda is therefore meant to increase. Does that make sense? Okay. But I know that v is equal to f lambda. Okay. But what is this thing doing over here? Okay. But f is inversely proportional to lambda. So if my lambda is increasing, my frequency, like I've been asked, the change that is made to the frequency should be lowered. We need a lower frequency for this to make sense, right? So to maintain the same speed of sound produced, we actually need a lower frequency for that to make sense. Does it make sense? So let's just write that down in words. So the distance x from node to antinode is longer, right? So lambda is also longer, okay? But v is equal to f lambda, and since v is constant, f will be inversely proportional to lambda. Hence, the frequency will be lowered. That's basically it. That's the goal of problem solving, step by step, until you arrive at the conclusion. Define electric potential difference. Okay. Electric potential difference is the energy transferred, right, per unit charge, okay, from electrical to other forms That's basically non-electrical, right? So before a coulomb of charge moves, it's going to get a bag of energy. And the energy that is transferred to it is what we refer to as electric potential difference. So component X is basically a heater. That is essentially what component X is. Okay. So that the PD across the resistor of resistance of that is 6 volts. Okay, so this is my resistor and I have my current. So I basically know a simple formula that should be able to tie those two things together. That is basically V is equal to IR. So V is equal to IR. So V will just be equal to 0.86 multiplied by 7. That's going to give me 6.02. In other words, that's the same as 6.0 volts. Okay. Determine the current I1. Current I1 is the current going through to that thing. Okay. So 6 volts has gone to this resistor. So for this whole combination, right, for all of this, I'm left basically with 230 minus 6 to share amongst this and this. You know that if things are in parallel, they're going to have the same amount of voltage. So 230 minus 6, that's 224. So across this component, this setup, you're going to get 224. Across this, you're going to get 224. So now you can see if I get 224 across this, and there's only one of it, I can therefore be able to calculate I2. And using Kirchhoff laws, I know that this current of 7 has to split into I1 and I2. Right? So first let's find I2. Let's do that. So I2 will basically be equal to V is equal to IR. So that's V over R. And that's basically going to be equal to 230 minus 6.02 divided by 170. So I2 is basically 1.3175. If you therefore then want to get that, you know that 7 is equal to I1 plus I2. So I1 is basically 7 minus 1.3175. The difference of that is actually 5.68247. That's 5.7. So what I'm doing is I'm just connecting I1 and I2 to be able to get I1. Hope that makes sense. the PD across component X. PD across component X. So now I have I2 and I have I2 and I1 and the resistance of that. So I can be able to find the V across this. These two guys are supposed to share 224. So PD across V should not be that difficult. Okay, so I know that the PD across the 2.4 resistor is basically going to be equal to IR. So that's basically going to be 5 point, guys, I love electricity, right? Electricity, you just need to follow the circuits and you should be able to get a correct answer. So this is going to give me 13.6 volts. That's what the 2.4 resistor is getting. So the PD that X is going to get is just going to be equal to 224 minus 13.6. As simple as that. So we get about 210.38. That's going to be 210 overall. 210. Okay. Calculate the power dissipated in component X. Power VI. V times I. So that's 210. The current across X is still that same value of I, which is 5.68, 247. You're going to get a power of 1,200 watts. Okay. Cool. The purpose of that power is to provide, the purpose of the circuit is to provide power to component X. So basically, useful power output over power input times 100. That's the formula for efficiency, guys. Okay, so the purpose of that circuit itself is powered by that little battery that you were seeing over there, that little power source that was saying 230, right? That was the power source powering all of that. So the power input itself is going to be VI as well. So it's 230 times 7 that's coming out. So if you go here, it's 230 times 7. That's the power that we are essentially getting, right? And if you don't understand why we're saying power is equals to VI, a little help for you. Power is basically the work done per unit time. But the work done is actually, if you think about it, the work done, V is the work done per unit charge. So V is the work done per unit charge. So work done is VQ. So if I have power being equal to VQ over T, Q over T is current, right? Current, the rate of flow of charge. So power will be equal to VI. That's where we get power is equal to VI. That's why I'm using that formula. In case you're wondering, but where is this guy getting power is equal to VI from, right? So my useful power output is actually 1,200 divided by 230 times 7 times 100. Punch that in your calculator and you're going to get about 75%. Okay, that's cool. Hope that makes sense. The resistor of resistance 170 is removed, leaving an open circuit. There is no change to the resistance. State whether the current remains the same. Okay, so current in the power supply. So V is equals to IR. Okay, so if I go here, my power supply is still the same. So using V is equals to IR, I want to figure out what happens to I. That's my goal. So V is equals to IR. Right, I want to figure out what on earth is happening to the value of R. As all of this is happening. Okay, so I know that V is constant. So this is constant. It's still 230. But the value of R, something interesting happens here, right? I know that if I have a combination of resistors in parallel, the total resistance, the total effective resistance that I'm getting from the setup will be less than the smallest resistor. That's a fact, right? If you were to do the math, try to find the, I'll leave you to find the resistance of component X. You already know that it's getting a certain value. You know the current that's present. I want you to get the resistance for it, right? Simple calculation. You're going to get a very high value. And I want you to do 1 over 1 over 1 over 1 over all of those things, and then get the total resistance. You're going to find out that it's smaller than the smallest resistor possible because you're adding fractions of all the different things, right? So if you're to remove 170, you're going to be left with a series setup, right? So by removing that, all of this is going to go, right? And if all of this is gone, you're only left with a parallel setup where we're just adding 2.4 and that. So by the very nature of that, the resistance in this setup is going to shoot. It's going to increase too much. And because we have a high resistance, V is the same. I will be equal to V over R. A bigger value of R means a smaller current, right? So the current decreases. Does that make sense? So removing the 170, remember, if you have three things in parallel, the total resistance for a parallel setup is going to be lower than the smallest resistor. And removing one of those setup means I'm left with a series setup where you just add two things up and they're going to have a very greater resistance. So overall, your current is going to decrease. So I can therefore say, what happens to my current? Well, my current decreases. That's what happens. So my current decreases. That's what happens. Okay. Compare an alpha particle with a beta plus particle in terms of their masses and charges. So compare and contrast. Right? So compare doesn't really mean just give the differences. You can also give what's similar between these two things. But at the top of my head, the mass of an alpha particle, right, is greater than the mass of a beta. Sorry, English is escaping me here. Of a beta plus particle, right? That's a fact. That's something that we know exists. Okay, we know that the magnitude of an alpha particle, the magnitude of an alpha particle is greater than the magnitude of charge on a beta plus particle. That's also another fact, right? So the magnitude of charge, an alpha particle, basically, if you know it, that's an alpha particle. That's a beta plus particle plus 1. That is 2 plus, right? So we know that the magnitude of the charge on one thing is greater than the other thing. But what's also similar, what's interesting about these two things is that they are both positively charged. They are both positively charged. Right? There's another distinction that you can be able to make for these two kind of particles. So you've compared the mass, you've compared the charges, and you've stated that both of them are actually quite in fact positively charged, which is very, very important in this distinction, because by comparing, you're not only stating the differences, but also what's similar. You're comparing. The comparison can be both of them are tall, but I'm comparing them. I'm making an observation and stating what I'm seeing. Right? Or the differences. One mass is greater than the other, one charge is greater than the other. I hope that makes sense. Part B, we're almost done. This is our last question, and we'll call it a day. Nucleus P undergoes alpha decay to form nucleus Q. So we've been asked to draw and label a cross to show the proton number and nucleon number of Q. Okay, let's get to that. So what is P? We know that P is actually 216 and 84, and an alpha particle is basically 42. So if it's going to lose that, we expect 216 to decrease by 4 to 212, 84 to decrease by 2 to 82. So you draw a cross at 212 and 82. That's going to be Q. Okay. So the name of particles emitted is Q decays to form R. So Q over here wants to decay and form R. So that's 82 and going to 83. So this is Q, right? And I know that R is again the same, 212, but 83. So what particle do you need to emit in order for your proton number to increase by 1? And we know that it has to be a beta negative particle. But the question says, state the name of particles. Physics is very particular with the way they phrase their questions. So in this case, the particles that we have is indeed a beta minus particle. But we know that's not it. We've learned that another particle is released during beta minus decay. And that is an electron antineutrino. Right? Okay. Next up, before the alpha decay, P is traveling at a constant velocity After the decay, q has a velocity of 1.3 times 10 to the power of 5 at an angle of 68 degrees to the original path of p. The alpha particle has that velocity, and our goal is to find the angle theta. What does the principle of conservation of momentum say? It states that momentum either in the y and the x before and after is equal, is conserved. So momentum, the principle of conservation of momentum tells us that momentum before the collision is equal to the momentum after the collision. So what we have to do is look at momentum before and momentum after. But because they're two axes, we're going to look at momentum in the y as well as look at momentum in the x. So look at those two different scenarios. So if I were to resolve this in the y, I'm going to have 150 times 10 to the power of 5 sine theta. We've talked about the sine, guys. Sine, cos, resolution. We've done this before, right? If you go here, we have 1.3 times 10 to the power of 5 times sine 68. So we have two momentums, two velocities rather, one up, one down, and we can find two momentums, one up and one down. And these are momentums in the y. You solve for y separately, then you solve for x. And I can't look at x because I don't know the velocity that the p particle is moving at, right? It's going to be quite difficult to do that because we have an original path of the p. But what we're going to do is resolve momentum in the y and therefore be able to create momentum before with momentum after. So how are we going to do that? Is we're going to say momentum before is equal to momentum after, and momentum is basically mass times velocity before it's 0, because there is no momentum in the y-axis itself before the collision, of course. So 0 is equal to momentum after. We have q, that's actually 212. 212 u is the mass of q. So 212 u times, what is the velocity? 1.3 times 10 to the power of 5 times sine 68. Minus, because I'm going to have two different directions, right? I'm just doing it for convention. One is up, one is down, two different directions. The alpha particle, what's the mass of an alpha particle? It's 4 times the atomic mass unit, which is 4u. That's where you know what u is, guys, right? It's the atomic mass unit times 150 times 10 to the power of 5 times sine theta. So my sine theta is, or rather, let's just get to the straight to the point because we don't have a lot of space. Arc sine of theta. So theta is going to be arc sine of, so this goes to the other side. So it's 212 u times 1.3 times 10 to the power of 5 times sine 68 divided by 4u times 150 times 10 to the power of 5. That's it. Okay, cool. We close that off. Okay, that's basically our answer. So let's just say times 1. Okay, cool. So you punch this in your calculator, you're going to get a value of theta of 25.02067. That's 25 degrees, right? And what I'm doing is basically momentum before is equal to momentum after in the y. Momentum before is 0. Momentum after, I equate that and try to solve for theta. The rest is just mathematics. The last question, kinetic energy of the alpha particle. I know that kinetic energy is actually 1/2 mv squared, right? So what I'm going to do is I'm going to say what's the mass of an alpha particle. We talked about this. 1/2 times 4u times v squared. So we have 1/2 times 4. I know what u is. Times 1.66 times 10 to the power of negative 27. The velocity of the alpha particle, we'll look for it. We've been given 150. Nice. 150 times 10 to the power of 5 squared. We punch that in your calculator. We get 7.5 times 10 to the power of negative 13. So 7.5 times 10 to the power of -13. And that'll be it. That'll basically be it. I hope if you made it this far, you've enjoyed the video. If there's anything that was unclear, put it down in the comment section below and I'll be able to address that. And I hope this is really helpful for you guys. And if you like the video, put a thumbs up and subscribe so that we can be able to see, you can be able to see more content. Thank you guys for watching, and I'll definitely see you in the next one.